September 6th, 1976. Hakodate Airport, northern Japan. Rain hammers against the tarmac as ground crew stare at the massive silver aircraft that has just landed without permission. Lieutenant Viktor Belenko's hands still shake as Japanese officials approach his MiG-25 Foxbat. The Soviet pilot has just completed the most consequential defection of the Cold War, delivering the USSR's most secretive interceptor directly into Western hands. Within hours, American intelligence officers arrive. Within days, they begin dismantling the aircraft in a hangar, photographing every component, measuring every system. Within weeks, their initial reaction shifts from excitement to confusion to outright mockery. Captain Harold Fisher, a U.S. Air Force intelligence analyst with 15 years of experience, opens the avionics bay for the first time. He expects to see the cutting-edge, solid-state electronics that power American F-15s and F-14s. Instead, he stares at rows of glowing vacuum tubes, the same technology his grandfather's radio used in 1945. They're using tubes, he tells his commanding officer, barely containing his laughter. The whole damn thing runs on tubes. What Fisher didn't know was that those vacuum tubes represented one of the most brilliant engineering decisions of the Cold War. What American analysts dismissed as Soviet backwardness was actually a calculated advantage that would make the MiG-25 nearly invulnerable to the single greatest threat of nuclear warfare. Within months, as technical teams completed their analysis, initial mockery would become grudging admiration. Within years, some American engineers would quietly admit the Soviets had been right all along. The story of the MiG-25 Foxbat begins not in 1976, but 14 years earlier, when American aerospace engineers achieved what seemed impossible. On December 22, 1964, Lockheed's SR-71 Blackbird made its first flight, a titanium marvel capable of sustained flight at Mach 3.2 and altitudes exceeding 85,000 feet. The aircraft could cross the Soviet Union in less than 6 hours, photographing military installations with impunity. Soviet air defenses, among the most sophisticated on Earth, proved utterly inadequate. Marshal Pavel Batitsky, commander of Soviet Air Defense Forces, watched radar screens track the SR-71's impossible speed across Siberian airspace in early 1965. His MiG-21 interceptors topped out at Mach 2.05. His surface-to-air missiles couldn't reach above 70,000 feet. The Americans were making a mockery of Soviet sovereignty, and Batitsky knew it. "We are blind and deaf," he told the Politburo in March 1965. "The Americans fly where they wish, photograph what they wish, and we can do nothing." The Mikoyan Gurevich Design Bureau received an emergency directive: create an interceptor capable of destroying the SR-71. Chief designer Mikhail Gurevich, then 67 years old, assembled a team led by 38-year-old Rostislav Belyakov. Their challenge was unprecedented. The aircraft needed to reach Mach 3, climb to 80,000 feet, and carry missiles capable of destroying a target moving faster than a rifle bullet. It needed to do this while Soviet industry struggled to produce the advanced materials and electronics that made American aircraft possible. Belyakov made a decision that would define the MiG-25's legacy. Rather than attempt to match American technological sophistication, he would embrace brute force. The MiG-25 would be built primarily of nickel-steel alloy, not titanium. It would use two massive Tumansky R-15BD-300 engines, each producing 24,700 pounds of thrust with afterburner. And critically, its avionics would rely on vacuum tube technology that American engineers had abandoned a decade earlier. The decision seemed insane to Western observers who later learned of it. Vacuum tubes were heavy, bulky, and power-hungry. They generated enormous heat. They represented everything obsolete about 1940s technology. But Grigory Kisunko, the chief designer of the RP-25 Smerch radar system, understood what his American counterparts did not. Solid-state electronics are fragile, he explained to skeptical military officials in 1966. One electromagnetic pulse from a nuclear detonation and your transistors become sand. Vacuum tubes keep working. The irony was profound. American engineers had rushed to adopt transistorized systems precisely because they seemed more advanced, more reliable, more capable. They built aircraft around the assumption that future wars would be conventional, that nuclear weapons were deterrents rather than tactical realities. Soviet engineers designed for the war they expected to fight, a war where battlefield nuclear weapons would turn sophisticated electronics into useless junk in microseconds. Construction of the first MiG-25 prototype began in early 1964 at plant number 155 in Moscow. The aircraft took shape as a study in contradictions. Its fuselage was 80% nickel steel, welded together in sections like a submarine hull. Only the leading edges used titanium, unable to withstand temperatures exceeding 300 degrees Celsius at sustained high speed. The engines were monsters, designed to push the aircraft to Mach 2.83 in normal operations, with emergency capability to reach Mach 3.2 for short bursts before the engines destroyed themselves. Test pilot Pyotr Ostapenko climbed into the cockpit for the first test flight on March 6, 1964. The MiG-25 weighed 20 tons at takeoff, nearly double a MiG-21's weight. Ostapenko advanced the throttles and felt the R-15 engines shake the entire airframe. Like riding a controlled explosion, he later recalled. The aircraft accelerated down the runway at Zhukovsky Air Base and leaped into the air, climbing at a 60-degree angle. Ostapenko reached 30,000 feet in 90 seconds. At 50,000 feet, he lit the afterburners and pushed toward Mach 2.5. The steel skin heated until the cockpit temperature reached 40 degrees Celsius despite insulation. But the aircraft held together, stable and controllable, even as it punched through speeds that would have torn apart most conventional fighters. The RP-25 Smerch radar, mounted in the aircraft's nose, could detect bomber-sized targets at ranges exceeding 100 kilometers. Its vacuum tube construction required 600 individual tubes of various types, from tiny signal amplifiers to large power tubes that glowed cherry red during operation. The system consumed 16 kilowatts of electrical power, requiring dedicated generators driven by the engines. American radar systems of equivalent capability used perhaps 50 transistors and consumed a tenth the power. But those American systems had a fatal flaw that Soviet engineers had ruthlessly exploited. Alexander Berezniak, the electronics chief for the MiG-25 program, conducted a simple test in 1967. He placed a transistorized radar unit from a captured American drone in a shielded chamber. Then, he subjected it to an electromagnetic pulse equivalent to a 10-kiloton nuclear detonation at 5 kilometers distance. The transistors failed instantly, their delicate junctions destroyed by the surge of electromagnetic energy. He repeated the test with a vacuum tube unit. The tubes flickered, glowed brighter for a moment, then resumed normal operation. "This is why we build with tubes," he told his engineering team. "Because in nuclear war, only tubes survive." Production of the MiG-25 began in 1969 at Gorky Aircraft Plant No. 21. Soviet industry produced 1,186 MiG-25s in various configurations between 1969 and 1984, including interceptor, reconnaissance, and trainer variants. Each aircraft cost approximately 6 million rubles, roughly equivalent to $12 million at official exchange rates. The interceptor variant, designated MiG-25P, carried 4 R-40 air-to-air missiles, massive weapons weighing 475 kilograms each, and designed specifically to destroy high-altitude bombers and reconnaissance aircraft. Colonel Alexander Beshevets received his MiG-25P in March 1972 and reported to the 64th Fighter Aviation Regiment stationed at Belaya Air Base near Moscow. His first familiarization flight revealed the aircraft's brutal character. The MiG-25 didn't fly so much as barely contained itself. At full power, fuel consumption reached 15,800 kilograms per hour, draining the aircraft's tanks in less than 90 minutes. The cockpit instruments were crude by Western standards, dominated by mechanical gauges and analog displays, but Beshevets learned to trust the aircraft's raw capability. "It climbs like a rocket," he wrote in his flight log. "Nothing else matters when you're racing towards 70,000 feet to intercept a target." American intelligence agencies tracked MiG-25 deployments with growing concern. CIA analysts noted that Soviet air defense forces positioned MiG-25 regiments along likely SR-71 flight paths. The aircraft's existence forced American planners to fly reconnaissance missions at maximum altitude and speed, reducing photographic resolution and increasing mission risk. But without access to an actual MiG-25, American analysts could only speculate about its capabilities. They assumed Soviet electronics matched Western standards. They assumed advanced materials and manufacturing techniques. They assumed, incorrectly, that the MiG-25 represented a peer competitor to American technology. That assumption shattered when Viktor Belenko made his decision to defect. The 29-year-old senior lieutenant had grown disillusioned with Soviet life after years of watching the gap between party propaganda and reality. He had flown the MiG-25 for 2 years with the 513th Fighter Aviation Regiment based at Chuguyevka Air Base in the Soviet Far East. On September 6, 1976, he was scheduled for a routine training flight. Instead, he pointed his aircraft east toward Japan and descended to low altitude to avoid radar detection. Japanese air defense radar picked up Belenko's MiG-25 as it crossed into their airspace at 500 feet altitude. Fighter aircraft scrambled to intercept, but Belenko transmitted on emergency frequencies that he was defecting. He landed at Hakodate Airport without permission, narrowly missing a commercial airliner on final approach. Within 2 hours, Soviet diplomats demanded the aircraft's immediate return. Within 6 hours, American intelligence officers were boarding flights to Japan. Within 3 days, a U.S. Air Force cargo aircraft transported the disassembled MiG-25 to Dayton, Ohio, home of Wright-Patterson Air Force Base and the Foreign Technology Division. Major Robert Johnson led the technical analysis team that began examining the MiG-25 in September 1976. Johnson had spent his career analyzing Soviet aircraft technology. He had helped evaluate captured MiG-21s from defecting pilots in the 1960s. He expected the MiG-25 to represent a quantum leap forward in Soviet capability. Instead, he found himself staring at an aircraft that seemed to have been designed by engineers from 2 different eras. The airframe was crude but effective. Welding seams were visible throughout the structure. Access panels were secured with hundreds of individual screws rather than quick-release fasteners. The cockpit layout looked primitive, with instruments scattered across the panel in no apparent logical order. The ejection seat was a simple rocket-powered design that had barely evolved since the 1950s. But most shocking was the electronics bay. Johnson counted more than 600 vacuum tubes in the radar system alone. The weapons control system used another 200 tubes. Even basic flight instruments relied on tube-based amplifiers and signal processors. "I thought it was a joke," Johnson later told aerospace journalists. "We kept looking for the real avionics, the modern systems that must be hidden somewhere, but there was nothing else. The entire aircraft ran on technology that RCA had abandoned in 1965. Other analysts shared his disbelief. Here was an aircraft that could fly Mach 2.83, climb to 123,000 feet, and track targets at extreme range, all using electronics that belonged in a museum. The initial assessment reports reflected that mockery. Intelligence summaries described the MiG-25 as evidence of Soviet technological inferiority. Aviation Week published articles suggesting Soviet industry remained decades behind American capability. Fighter pilots training to face MiG-25 SEF were told not to worry about the antiquated systems. The vacuum tubes became a punchline in briefings, proof that Soviet engineers couldn't master modern electronics. But a smaller group of specialists began asking different questions. Dr. Paul Tsesis, an aerospace engineer consulting for the Air Force, examined the radar system specifications more carefully. The RP-25 Smerch could detect targets at 100 kilometers range and track them through violent maneuvers. It could guide missiles against targets flying at Mach 3 at altitudes where the air was thinner than the vacuum inside those Mach tubes. And it did all this while generating enough electromagnetic power to burn through enemy jamming and countermeasures. CG ran calculations on the radar's power output. The vacuum tube design allowed peak power transmission of 1 megawatt, 10 times higher than equivalent transistorized systems. That power advantage translated directly into detection range and jamming resistance. American F-15 radars might be more sophisticated, but they couldn't punch through the kinds of electronic warfare environments that nuclear battlefield conditions would create. The Soviets aren't behind, CG wrote in a classified memo in October 1976. They're designing for a different war than we are. The electromagnetic pulse question emerged as specialists dug deeper. Lieutenant Colonel William Greenwood, an Air Force nuclear weapons effects specialist, joined the analysis team in November 1976. He immediately recognized what the vacuum tubes represented: Greenwood had spent 5 years studying how nuclear weapons affected electronics. He had watched transistor-based systems fail catastrophically during high-altitude nuclear tests in 1962. He understood that solid-state electronics, for all their advantages in size and efficiency, were fundamentally vulnerable to the gamma radiation and electromagnetic pulses that nuclear detonations produced. Greenwood conducted a simple demonstration for skeptical colleagues. He placed a transistorized radio next to a vacuum tube radio. Then he subjected both to an electromagnetic pulse from a test generator, simulating the effects of a nuclear detonation at 20 kilometers distance. The transistor radio died instantly, its circuitry fused into silicon scrap. The vacuum tube radio continued playing, the tubes glowing slightly brighter for a moment before resuming normal operation. "This is what the Soviets understood," Greenwood explained. "In nuclear war, vacuum tubes don't just survive, they're the only things that survive." The implications rippled through American military planning. Soviet doctrine explicitly called for tactical nuclear weapons in any major European conflict. The MiG-25's vacuum tube design meant it could continue operating in environments where American aircraft would be flying blind, their sophisticated electronics reduced to dead weight. The crude mechanical instruments that American analysts had mocked suddenly made sense. When electronic displays failed, Soviet pilots would still have basic flight information from pressure-driven gauges and mechanical compass systems. Testing continued through late 1976 and early 1977. Engineers measured every aspect of the MiG-25's performance. The R-15 BD-300 engines proved to be exactly as brutal as their specifications suggested. At full afterburner, they consumed fuel at rates that limited the aircraft's combat radius to 300 kilometers. But those engines could push the MiG-25 to speeds that made interception nearly impossible. Test pilots at Wright-Patterson flew simulated intercept profiles, attempting to imagine themselves attacking an SR-71. The profiles worked. Given proper warning and positioning, a MiG-25 could indeed threaten the Blackbird. The aircraft's altitude capability particularly impressed American test pilots. Captain Richard Fletcher flew the MiG-25 to 80,000 feet during test flights in February 1977. "You can see the curvature of the Earth," he reported. "The sky above is black even at midday. You're in space, essentially, still flying an aircraft that weighs 20 tons. The view was spectacular. The performance was undeniable, and the vacuum tubes hummed along, powering systems that tracked targets and guided missiles in an environment where American electronics would struggle." Heat emerged as both the MiG-25's greatest challenge and a key advantage of vacuum tube design. At Mach 2.83, aerodynamic heating raised the aircraft's skin temperature to 290 degrees Celsius. Fuel tanks became heat sinks, with fuel temperatures reaching 55 degrees Celsius before being injected into engines. The cockpit required active cooling to keep the pilot from being cooked alive. In this inferno, solid-state electronics would have failed from thermal stress alone. Vacuum tubes, designed to operate at temperatures exceeding 200 degrees Celsius in normal operation, barely noticed the additional heat. The reconnaissance variant, designated MiG-25R, revealed additional sophistication. This version replaced missiles with cameras and electronic intelligence gathering equipment. Soviet engineers had designed the camera bay to maintain precise thermal control, using heat exchangers and insulated compartments to keep film at stable temperatures even as the airframe heated to dangerous levels. The reconnaissance systems could photograph targets from 70,000 feet with resolution sufficient to identify individual vehicles and buildings. Israeli fighter pilots learned to respect the MiG-25R during the 1970s. Soviet advisors deployed MiG-25R aircraft to Egypt and Syria, conducting reconnaissance missions over Israeli territory at speeds and altitudes that made interception impossible. Israeli F-4 Phantoms, among the most capable fighters in the world, couldn't touch them. Lieutenant Colonel Eitan Ben Eliyahu, a top Israeli pilot, attempted multiple intercepts. "We climbed as high as we could, pushed our engines to maximum, and watched them fly overhead like we were standing still," he later recalled. "It was humiliating." The October 1973 Yom Kippur War demonstrated the MiG-25's capabilities in combat conditions. Soviet-operated MiG-25Rs flew reconnaissance missions throughout the conflict, providing Arab forces with real-time intelligence on Israeli positions. Israeli air defenses, among the world's most sophisticated, managed to engage MiG-25s on several occasions. They achieved no confirmed kills. The aircraft's speed and altitude rendered even advanced surface-to-air missiles ineffective. Israeli Hawk missiles, designed to engage targets at 60,000 feet, couldn't reach the MiG-25s operating above 70,000 feet. By the time radar operators detected the aircraft and launched missiles, the MiG-25 was already beyond engagement range. American analysts studying these engagements reached uncomfortable conclusions. The MiG-25 might be crude, but it was effective. Its vacuum tubes might be obsolete, but they were reliable. Its steel construction might be heavy, but it was durable. The Soviets had built an aircraft optimized for its specific mission, and that aircraft worked exactly as intended. The field maintenance advantages of vacuum tube design became apparent as American mechanics worked with the MiG-25 throughout 1977. Sergeant Thomas Bradley, an avionics specialist with 20 years of experience, found himself relearning skills he hadn't used since technical school. Vacuum tubes are simple, he explained to newer technicians. They either work or they don't. You can test them with basic equipment, you can replace them with a screwdriver, try that with a circuit board full of transistors. Soviet maintenance manuals reflected this philosophy. Field repair procedures assumed access only to basic tools and test equipment. Technicians at remote Arctic bases could service MiG-25s using the same equipment used to repair World War II-era radar systems. The radar's liquid cooling system, another feature that seemed primitive to American engineers, proved brilliantly effective. Rather than rely on forced air cooling that would have been inadequate at high altitude, Soviet engineers pumped ethyl alcohol through cooling channels surrounding critical vacuum tubes. The system could dissipate 30 kilowatts of heat, keeping tube temperatures within operating limits even during prolonged high-power radar operation. When the alcohol supply was exhausted, maintenance crews could refill the system with pure vodka in emergency situations. American engineers reluctantly admitted the system was both crude and effective. Intelligence assessments evolved as understanding deepened. Initial reports emphasizing Soviet backwardness gave way to more nuanced analyses. A classified CIA study completed in June 1977 concluded that the MiG-25 represented a different engineering philosophy rather than inferior capability. The report noted that Soviet designers had optimized the aircraft for nuclear war scenarios that American planners had largely dismissed. "We designed aircraft to win," the report stated. "They designed aircraft to survive." The numbers backed up that assessment. Soviet factories produced 1,186 MiG-25s between 1969 and 1984, deploying them to units throughout the USSR and exporting variants to allied nations, including Algeria, India, Iraq, Libya, and Syria. The aircraft served on every Soviet border, from the Arctic Circle to the deserts of Central Asia. Pilots learned to manage its brutal characteristics, to compensate for its crude systems, to exploit its overwhelming speed and altitude advantage. And those vacuum tubes kept working, year after year, in conditions that would have destroyed solid-state electronics. Iraq's experience with the MiG-25 during the Iran-Iraq War and later conflicts demonstrated the aircraft's resilience. Iraqi pilots flew MiG-25s on reconnaissance and strike missions throughout the 1980s, operating in harsh desert conditions with limited maintenance support. The vacuum tube avionics proved remarkably resistant to sand and dust that destroyed more sophisticated electronics. Iraqi technicians learned to service the systems using basic tools and locally manufactured replacement tubes. When Iraqi MiG-25s defected to Iran in 1984 and 1991, Iranian engineers examined the aircraft and reached the same conclusions American analysts had 15 years earlier. The technology was old, but it worked. The final intelligence assessment on Belenko's MiG-25 was completed in August 1977, 11 months after the aircraft landed in Japan. The United States returned the disassembled aircraft to the Soviet Union in carefully packed crates, but not before photographing every component, measuring every dimension, and testing every system. The lessons learned fundamentally changed American understanding of Soviet military technology. General Robert Dixon, commander of Tactical Air Command, summarized those lessons in a briefing to the Joint Chiefs of Staff in September 1977. "We assumed Soviet engineers built the MiG-25 with vacuum tubes because they couldn't build something better," Dixon stated. The truth is they chose vacuum tubes because they understood something we forgot. In nuclear war, sophisticated electronics are a liability. Simple, robust systems survive. The Soviets designed for the war they expect to fight. We need to reconsider whether we've done the same. That reconsideration led to significant changes in American aircraft design philosophy. Engineers working on the F-15 and F-16 programs added electromagnetic pulse hardening to avionics systems. Military specifications began requiring that critical flight systems maintain operation after exposure to nuclear weapon effects. Backup mechanical instruments were retained even as glass cockpits and digital displays became standard. The lessons learned from mocking Soviet vacuum tubes influenced American military aviation for decades. Viktor Belenko, meanwhile, settled into life in the United States. The CIA paid him a substantial sum for the MiG-25 and his intelligence debriefings. He became an American citizen, worked as an aerospace consultant, and occasionally gave lectures about his experience. In interviews years later, he expressed surprise at the American reaction to his aircraft's technology. Soviet engineers were not stupid, he told an aviation magazine in 1998. They built what they needed to build. If vacuum tubes worked better for the mission, they used vacuum tubes. Americans always assume new technology is better technology. Russians know that working technology is better technology. The MiG-25 remained in Soviet and Russian service until the early 2000s. Later variants included improved engines, better weapons, and updated radar systems that finally incorporated solid-state electronics protected by heavy shielding. But many aircraft continued flying with their original vacuum tube systems, a testament to the durability of the design. The last Russian MiG-25s were retired in 2013, having served for 44 years, far longer than the decade or two that most fighter aircraft remain operational. Colonel General Alexander Zelin, commander of the Russian Air Force, spoke at the retirement ceremony for the final MiG-25 regiment in May 2013. This aircraft represented Soviet engineering at its best, Zelin said. Not the most elegant, not the most sophisticated, but brutally effective at its mission. Those who mocked its vacuum tubes did not understand that effectiveness comes in many forms. The MiG-25 defended Soviet airspace when nothing else could. That is the only measure that matters. American pilots who studied the MiG-25 after Belenko's defection eventually reached similar conclusions. The initial mockery faded as understanding grew. Captain Harold Fisher, the intelligence analyst who first opened the avionics bay and laughed at the vacuum tubes, wrote a retrospective analysis in 1995. "We were arrogant," Fisher admitted. "We assumed our way was the only way, our technology the only valid approach. The Soviets taught us that engineering is about solving problems, not showcasing sophistication. They had a problem, how to build an interceptor that could survive nuclear war. They solved it with vacuum tubes. We laughed. They were right." The story comes full circle to that rainy day in September 1976, when Viktor Belenko taxied his MiG-25 to a stop on a Japanese runway. The aircraft that American engineers would mock for its vacuum tubes represented one of the Cold War's great engineering achievements. It flew higher and faster than almost any other fighter aircraft in history. It remained operational in conditions that would have disabled more sophisticated designs, and it did so using technology that seemed primitive but was actually brilliant in its appropriateness for the mission. What American pilots couldn't believe when they first examined the MiG-25's vacuum tubes was that Soviet engineers had made the right choice. What took years to understand was that sophisticated doesn't always mean better. What the Cold War taught, through the example of one defector's aircraft, was that engineering excellence comes from matching technology to mission requirements, not from blindly pursuing the newest and most advanced systems available. The MiG-25's vacuum tubes, glowing softly in their avionics bay, had been telling that story all along. It just took American engineers 11 months of careful analysis to hear what those tubes were saying.